today is at least the first one, and the one that gave the ITC colloquium, which was very revealing about the collapsing stars, is Carl Fields, and he is joining us remotely from Los Alamos. Sorry, from NANL. And he will tell us more about the Mesa Web, the cloud resource for stellar evolution and astronomy, which is a more standard astrophysics topic of how stars evolve. After him, the next speaker would be Evan Bauer from the CFA, and he will tell us about phase separation in crystallizing white dwarf plasma mixtures. That is of great relevance to us because the sun will get there at some point, a few billion years from now. And then Joseph Guidry is visiting from Boston University, not very far away. Where is Joe? Joe?
Yeah, sure.
Joe. And he will tell us about ancient planetesimals colliding around white dwarfs again. So white dwarfs are highlighted today. And finally, Jesse Ham from Harvard just sent me an email with a different title. One second, I'll find the title. Just before this, let's see, here it is. The title is A Galactic Mystery Unwarped. So we are all excited about that. We'll hear it at the end. Go ahead, Carl. We hear you. You should unmute yourself, of course, Carl.
Carl, go ahead.
He's muted, Mark. He might maybe speaking.
Okay, go and get started.
Yeah. Okay. Yeah.
Is that yes? Sorry, I couldn't hear.
Yes.
Am I getting started? All right, you guys are muted. Sorry.
Yeah, you can start.
I can.
Go ahead.
Okay. Cool. Yeah. So thanks for inviting me to talk with y'all today. This is a much shorter talk, of course. Yeah, I wanted to share today a bit about Mesa Web. So this is a little bit different outside of my research that I talked about earlier for those of you that attended. Today I want to talk about Mesa Web. It's a cloud resource for stellar evolution and astronomy curricula. I want to talk about some of the things that it features, some of the things we're trying to push on forward, and some of the things you might see in an article coming up pretty soon. For those that weren't at the talk earlier, my name is Carl Fields. I'm a RPF Distinguished Postdoctoral Fellow at Los Alamos National Lab, working in the CCS2 division. And my background is primarily on stellar explosions of massive stars. So I want to start off before I get into detail. Hopefully I'm showing the correct view of these slides. Some of the ways that 1D models have been used in the past, coupling with observation. So one of the ways that I think about are these grid of 1D explosion models by Sean Couch. The STIR model, as he named it, simulating turbulence in reduced dimensions, where the population from the histogram is generated using 1D explosion models. And then overlaid on top of that is a neutron star mass distribution with a solid white line inferred by observation. And so on the x-axis we have gravitational weight, or gravitational mass. I'm not talking about gravitational weight anymore. And the PDF is, it's a PDF in terms of arbitrary units. So one of the, this is one of the ways that we've been able to say, okay, can we explode a bunch of models of additional masses and produce something that looks like what we expect from observation. So that's what folks have done before. I'm also reminded of Gene Choi's work in 2016, the Mesa isochrone stellar tracks, the way that that's been coupled with observations to make estimates for exactly what globular clusters. And so there are a lot of ways that 1D models are leveraged in terms of stellar evolution, core collapse, and so they're very valuable in a number of ways. So one of the things that is required with stellar models is connecting stellar models and observables, right? So you have to choose these inputs that are loading out of order. Some of them include mass loss, parameterizing your convection, nuclear input data, so nuclear reaction rates, equation of state, these different types of things. Angular momentum transport, so how angular momentum is approximated in 1D rotating models, magnetic fields, wave sands. And so one of the things that you want to try to do is use empirical calibrations to sort of feedback and determine what are some good inputs for these. So a lot of work has been done, nuclear physics experiments, to determine cross sections at stellar environments that can be used as input for nuclear reaction rates. Of course, connecting to astrophysical observations when possible, as well as direct numerical simulations for things like hydrodynamics, convection. One of the ways that I've actually looked at this in the past is by running grids of 1D stellar models using Mesa and actually varying the reaction rate uncertainties to measure how much that varies the stellar properties. So on the right here, I have the carbon-12 mass fraction on the x-axis. The y-axis is the probability. So we have a probability density function here, where the variation is due to the uncertainty in a handful of nuclear reaction rates in a low-mass star. And so the dashed lines are the 68, 90, 95% confidence interval. But basically, it allows you to set limits within the uncertainties for the different nuclear reaction rates for things like the central carbon-12 mass fraction, something that might be relevant for something that is relevant for white dwarfs. It also allows you to identify key reaction rates. And so in addition to getting this distribution, you can actually you can perform what's called a Spearman rank order correlation coefficient. Some statistic basically where you compare the variation of a given property with the variation of the rate, and you can get something like either -1 or +1 for a positive or negative correlation. We found that for C12 alpha gamma. And so this is something that's been shown in the past for low mass stars. It's an important reaction rate. And so sort of showing unambiguously that our model allows us also to identify key reaction rates, which is something that's very valuable in scenarios where, say, it's less obvious which rates play a role. So in doing that, we were able to, again, this is sort of a similar approach, but with more, so varying more rates, 665 for nuclear reaction rates, extended to massive stars this time, 15 solar mass stars, where we were able to identify N14 P gamma as being an important rate on the property of the terminal age main sequence age. So this is something that's also been shown in the literature, so again, showing that this method, this statistic, is allowing us to determine which rates have the largest impact. You can't even see the square, it's at the top because it's a positive. It's a near perfect correlation. Okay, so that's some of the things I've done in the past with Mesa, and so sort of building on that, one of the things that really motivated me was how can we connect learners to state-of-the-art tools in stellar astrophysics so that they might be able to do either some of the research that I've shown in the past, investigate their own ideas about stars, but also just how could it be incorporated seamlessly, or at least reducing more barriers to access in, say, an educational environment. And so that's where the idea of Mesa Web sort of came to be. It was originally hosted at Arizona State when I was an undergrad, starting back in 2015. It's now hosted at Rich Townsend's, quote, these are his words, his unintentionally archaic website, where you're able to go online, input a bunch of different initial conditions for your Mesa model, click a button, and it'll run that model for about 4 hours or till some custom stopping condition. And it supports many single star options, so there's things like mass, metallicity, rotation, different mixing, and so on. So this is a tool that's been in use since 2015 when it first came online, and we're constantly looking for ways to update it and extend its capabilities so that folks can leverage it in the classroom. But the idea is that it removes the barrier to access from having to, one, have a laptop that can run Mesa, two, having the technical expertise to install Mesa, which is oftentimes not very trivial. So this is again one way that folks can do it with just an interconnect, with an internet connection and an email address. This is something that's been in collaboration with Frank Timmins at ASU, Max Zingali, Rich Townsend, and Aaron Dotter. We have an article writing up the details of Mesa Web that is waiting for a referee to say yes, it's accepted now. We just resubmitted the revisions, but so looking at the Mesa Web usage history, I think is a good metric for us as we've been adding things, adding capabilities and different tools to it. So I've led the development of Mesa Web. Early on, it was to help with another undergrad when I was an undergrad in Arizona State. But besides that, it was me and Frank for many years. And then I sort of have stepped down the past year or two. But previous to that, if Mesa Web went down, I was the person that you were in touch with, which was kind of stressful because it went down pretty often. I'd have to get my login, get to my laptop, and reboot the machine. So, but we've had some, I'd say, some great success. We've had over 1,400 unique users. That number is probably much larger now. And on the right, we have sort of a histogram of when we've added different things. We added MPEG files that come out. We have test suites that are sort of restarted but never finished. But the idea is that eventually you'll have the data that you can download the test suites and then analyze those data without having to run them yourself. Custom reaction rates, you can actually implement you can input your own custom reaction rate through Mesa Web portal. So this is something that allows people to use this as a research tool. And we also had some custom stopping conditions, right? What if you only want to evolve it for a little bit? You don't want to wait the 4 hours. You can set some stopping conditions, so mass or complexity or something. And one of the things I'm really excited about, though, is that one, it's on the new server at UW-Madison. So it has access to these capabilities that are much larger than what we had at ASU. But also, we are now trying to, along with this paper, create an online community hub for materials at Zenodo. So we have this space set up. Real quick, I'll just show sort of an example of the output here. So if you've never seen this before, this is a collection of plots made with PG Star and Mesa, which show convective history, stellar profiles, and so on. So this is something that will be returned with your model, packaged up as a movie when you submit your calculation. And folks have also used Mesa Web for research. And so this is an example of stellar tracks being used in a paper. It's on the archive of Mesa Web being used for research. So that just kind of brings home the point that now Mesa is seamlessly, in my opinion, being able to be used for research for folks that don't have an interest in learning how to use Mesa Web, but also that want to leverage it for education. And we want to incorporate more capabilities in the future, binaries, stellar explosions, stuff like that. And one of the things, this will be my last slide, I mentioned that community hub at Zenodo. I'm really excited about making a space where folks can share educational resources because there already exists the Mesa Marketplace where you can upload other different things for your Mesa Endless. This is a space we're creating where, okay, you use Mesa Web in the classroom, you have resources, whether it be homework, a Jupyter notebook or something. We're creating a space for that, and we're encouraging folks to contribute to that to again, help build this community and lower these access barriers in terms of education and leveraging Mesa Web. So with that, I'll end. Happy to answer any questions, and thanks again for the invitation.
Thank you very much, Carl. Can you give us an example of a problem, unsolved problem that could be very exciting in the context of using Mesa? What's the most interesting problem that you can think of?
I missed the first part of the question.
So can you give us an example of an unsolved problem that you think a tool like Mesa can address?
Oh, wow. Yeah, there's a lot of those. I think that one of the things I'm excited about is this sort of island of exploitability with these 1D stellar evolution models with massive stars. I think there's a lot of nonlinear behavior that takes place with convection and its approximations in advanced burning stages for massive stars. And that's something I think that I'm excited to sort of work towards with my multi-D convection models, and then use to inform 1D approximations for things like convection and so on. One of the things that's great about Mesa Web, I think that we sort of like to maybe brag about, is that the default settings are able to run a star from the pre-main sequence to the formation of the cooling white dwarf in less than 4 hours with the defaults it's set at. And so that's sort of the basis that we have for Mesa Web, that you have this access to be able to run these data, and sort of anything in between for a given resolution. So yeah.
Wonderful. Yes, go ahead, Evan.
Great talk, Carl. Do you have a sense of how many departments in the U.S. or worldwide are using this kind of in their classroom? I'm pretty sure Charles Alcock is using it here at Harvard this semester. But is it order 100, or do you know?
We had those data at some point. I want to say there were a handful of really consistent users. UChicago comes to mind. I want to say University of Pennsylvania, Harvard was definitely on that list, Santa Cruz. So there are definitely a list of folks that are actively been using it over the years. I don't know if we have as much of those data anymore since we switched. I think it'd be a really good metric. We're also always happy to hear how we can improve things, right? If you're using it and it's just like, well, I just really want Mesa Web to do this one extra thing, then I think that's something that's really doable too. So we're hoping to open that connection for communication with folks that are actively using it, and fostering this sort of Zenodo community, I think, maybe help with that.
Okay, any other questions? Charles?
I'm Charles Alcock, and I'm actually implementing Mesa with my teaching fellow in the undergraduate stars course, and it's actually been quite a revelation for us, certainly for me anyway. I did have a question actually. There are a number of other stellar evolution codes out there which are not general use. Has there been a systematic comparison of the results in different codes rather than changing the input, just change the code? I think it's an identity question.
Would you like me to repeat that, Carl?
Just the end. I think I got most of the beginning of the question. Yeah.
So from Charles Alcock, who was wondering if there's been a systematic comparison of different stellar evolution codes, and how, for example, does the Mesa output from something like Mesa Web compare to other codes with the same physical input?
Yeah, that's a great question. So we haven't done a benchmark in terms of like what we would argue or what we use for the Mesa Web defaults in terms of the pre-main sequence, one solar mass star to cooling white dwarf. There have been very rigorous studies, of which some of the primary authors are in the room right now, in comparing Mesa to other stellar evolution codes. And I think that we really rely on those rigorous tests that have been performed to have an idea of how Mesa and Mesa Web compares to things like Kepler and these other stellar evolution codes. So I really, there's a choice to choose between different Mesa versions when you use Mesa Web, actually. That's a new feature that Rich added. We want to extend that to, or at least continue to update that, and to potentially extend it to older, but it's much challenging because the endless change over time. So yeah, I would really defer to the great work that's been done by a lot of the lead developers compared to past codes, and the trust that the community has in the code because of that work.
Okay, last question, please.
So, do you have instabilities in the fully convective limit? I've been having issues when using some different versions of Mesa with the convective turnover times at the limit where stars become fully convective because of the pressure scale height diverging. And I don't know if you guys have that, and if so, if you do, how do you handle those?
I heard the second part of the question, I think, but not the first.
So I think Cecilia was wondering if there are instabilities when objects are fully convective.
Yes, in the convective turnover time.
And in particular with the convective turnover time?
Yeah, so I don't know if folks are already plugged into the Mesa user mailing list, but I think that that's a really good place because I have a lot of questions like this as well, in addition to the Mesa Marketplace where people have posted their in-list. So in terms of this particular physical scenario, I imagine that folks have looked into this. I don't have any particular details on that. The context that I've looked at in convection is more the advanced burning stages, in which I just say MLT doesn't work, and so I kind of defer. But yeah, and Evan may have some more insight on that as well, but be happy to chat offline if you wanted more detail on that.
Okay, thank you.
Thank you very
Thanks.
much. We have to move on.
Well, thank you, Carl.
Thank you so much.
Thank you. All right, can everyone hear me okay? Is the mic on? Yep. Great, so we'll continue with the Mesa theme for a little bit longer. Tried to tell Jesse he needed to change his talk to be about Mesa and white dwarfs as well, but he didn't have time. So I told him that 5 minutes ago. So I've been working here with Charlie Conroy and Aaron Dotter on big grids of Mesa models. You probably, or at least some of you have probably heard of the MIST project, Mesa isochrones and stellar tracks. So that's using the same code that Carl was introducing us to, but trying to make sort of state-of-the-art models across the HR diagram, particularly for timescales of evolution, all the way from the pre-main sequence, through the red giant phase and onto the white dwarf track. And I've been motivated a lot by improving the physics of white dwarfs in Mesa in particular, because if you think about making a big grid of models like MIST, most of them are going to end up in this phase eventually. And as Avi mentioned, the sun is one of those. It's actually many billions of years away from getting to this point. But eventually it'll shed its outer layers, it'll become a white dwarf. And that white dwarf will even crystallize once it cools off far enough to reach the freezing point. And we've kind of understood the basic physics of white dwarf cooling for a really long time. Leon Mastel has a great paper that we teach in our stellar evolution classes, that you can sort of think about a white dwarf in terms of this structure as an envelope and a core. And the envelope sort of mediates the rate at which heat escapes from the white dwarf, and the core contains that heat capacity. So this sort of proportionality here comes from just doing a basic envelope radiative transfer calculation, how fast is the heat leaking out, and then this differential equation is really just saying how much heat is there to extract as the white dwarf cools off and radiates it away at its luminosity. And so you end up with kind of a power law cooling time scale that white dwarfs do seem to follow reasonably reliably. But a little more goes on than just that. So if I go back to this picture again, you'll notice this is, by the way, not a simulation. This is an artist's picture for a Nature paper from the Warwick group about crystallizing white dwarfs. There's a guy named Mark Garlick who does a lot of great artwork for them. And one thing that we think white dwarfs do is eventually their cores cool down to a point where, because they're so dense, they crystallize and form a solid. And so that one thing that does is that releases latent heat. That means there's an extra energy source that will slow down the cooling for a little while. And so you see a pile up in the HR diagram of white dwarfs where they're slowing down their cooling for a little bit. But beyond that, it goes a little bit further. And actually, because white dwarf cores, we're pretty sure, and Carl mentioned in his talk 10 minutes ago, they're made of a mixture of carbon and oxygen. That's kind of sensitive to the details of burning during the helium burning stage. So you have some fraction of carbon and some fraction of oxygen, and it turns out that composition needs to rearrange itself when you go through a phase transition. You can think of this in terms of minimizing the free energy in a plasma. If I take a phase diagram, there's this nice plot from Zach Medine and Andrew Cumming, who have some good work on sort of multi-component phase diagrams. And if you ask, where does crystallization occur? It's where the free energy of the solid phase, once you cool to a point where the free energy of the solid phase becomes lower than the free energy of the liquid phase, then that phase is going to be preferred by minimizing the free energy. So here we've got green is representing solid and red is representing liquid. And if I stayed at fixed composition, I'd say I'm 70% of this x-axis is component 2 in their work. Think of this as oxygen. If I'm at fixed composition, maybe at this point I'd say, okay, the solid phase is lower than the liquid phase, so that's the phase I'm going to be in as solid. But actually, you can minimize the free energy further by taking that fluid element and separating it out into 2 components, one of which is over here in the solid phase, or sorry, this one is in the liquid phase. Yeah, so right here on the phase diagram, the red is lower than the green, so I guess I'd be in the liquid phase. So I'd have one over here that's maybe depleted a little bit of oxygen, and it's in the liquid phase, but there's then another component that is enhanced in oxygen, and that's in the solid phase, and those two are in equilibrium with each other, and I get a lower net total energy. And we kind of know about this in terrestrial context as well, right? Distillation is something we use to make stronger alcohols. There's actually something that people call freeze distillation. I was looking up to find a nice summary on the internet yesterday. I found a website called How to Moonshine. And this is apparently kind of the easiest way to start making concentrated alcohols. You could just freeze some wine, and if you discard the ice, that's less enriched in alcohol, and what's left over is more alcohol enhanced, and so it's more alcoholic. And I'm not sure I should say too much more because it might technically be illegal, and so I can't encourage you to go to this website, but it's so simple that I don't really know if that's going to be enforced. But there are actually sort of more advanced techniques than this that are used for making things like ice wines, freezing grapes. I think this also sort of concentrates the sugars, or there are ice ciders where apples can be left on the trees all winter. And so this is kind of a generic property of phase transitions that you separate into different compositions. In the context of carbon and oxygen mixtures, the phase diagrams look something like this. So now we're sort of on an x-axis again that is more oxygen-rich to the right. Pure oxygen's over here, pure carbon's over here. Our y-axis is given in terms of the melting temperature of pure carbon. And if you make a phase diagram, you get pairs of curves. So this is a nice plot from Simon Bluin has made a good recent phase diagram that is the pair of red curves. That's probably the most up-to-date calculation we have for that right now. So what happens in a white dwarf is you might be cooling at some composition that's, say, 60% oxygen, and you cool down until you hit this first phase diagram. This is what's called the liquidus, the phase transition of the liquid stage, and then it's actually going to separate out to a component that's more oxygen enriched in the solid phase. So there's this kind of gap where things have to separate out once you hit the liquid part of this phase diagram. What this looks like in action in a stellar evolution code is you might have a model that's, say, the core is to the left. You start crystallizing in the center because that's the densest part. So on this x-axis, the core is to the left and the surface is out toward the right. But I might have some amount of crystallized material that's going to be enriched in the oxygen. And if I evolve forward in time, then what happens is that crystallization front moves outward in the star. That also becomes enriched in oxygen. And to compensate and conserve elements, that means I have to push carbon outward. And carbon is lighter than oxygen. But this sort of liquid mantle surrounding the core is now underneath some heavier stuff. And so that actually excites a dynamical instability. And so there's this second add-on effect of mixing in the liquid mantle outside of the crystallizing core. So that's going to do some mixing, push carbon further outward. And the net effect then is moving oxygen toward the center, pushing carbon outward. I've implemented this in Mesa models in 1D stellar evolution code for white dwarfs. This is kind of what a typical starting carbon-oxygen profile might look like, pretty oxygen-rich in the core. Out here is the envelope. And as I start crystallization, you'll see this discontinuity at the location of the phase transition. That's propagating outward. You see the oxygen getting enriched in the core. There's some amount of mixing that's pushing the carbon outward further. And the net result is that we've transported oxygen toward the core and carbon outward with some amount of mixing in the intermediate regions until the final point where this is now all solid material with a much different composition profile than we started with. And I've recently posted a paper on arXiv about this. This is submitted to AppJ, ran a whole big grid of models, so this is kind of representative of that grid of different masses of white dwarfs. Darker line colors are more massive white dwarfs, but if I kind of toggle back and forth between here's the initial composition and kind of running this through the models, you see oxygen getting pushed toward the center. And that has actually a big effect on the energetics. In addition to the latent heat that will slow down white dwarf cooling, you get another sort of energetic effect of rearranging the compactness of the white dwarf and liberating more energy. So you get a cooling delay on the order of, it turns out it's only about half a gig a year. Sometimes you'll see in the literature more like a full gig a year. And so this is important for carefully getting cooling timescales of old white dwarf populations to be correct. But on top of that, there are a lot of other things that have recently started to be discussed in the context of crystallization and maybe other things that could be induced by that. So Matthias Schreiber has kind of a series of papers suggesting that this could be responsible for dynamos, starting to explain some of the statistics of why, for example, in CVs, there's a much higher occurrence rate of magnetic fields. And his suggestion is that the combination of kind of spinning up in accreting white dwarfs with this ongoing crystallization process can potentially contribute a dynamo and make a strong magnetic field, although I think this is very controversial. There's also sort of a literature about even longer cooling delays than this number I mentioned. There's a very metal-rich open cluster, NGC 6791, that seems to have at least a 2 gig a year, maybe longer cooling delay going on in its white dwarf population. Phase separation has been invoked in a Nature paper a while ago to try to explain some of this delay, but I think there's probably more going on there. Sihao Cheng had a really great paper a few years ago using Gaia DR2 to sort of measure kinematic ages of populations of white dwarfs. And he found a subset of massive white dwarfs seem to require a very, very long cooling delay that is associated with crystallization on the HR diagram, but on the order of 6 to 8 giga-years, which is a lot longer, an order of magnitude longer than that number I mentioned earlier. And one of the suggestions is that we really need to go to higher order mixtures and start including those phase separation calculations as well. So Simon Bluen has a nice paper about 3-component, what he calls distillation, which can dramatically enhance the concentration of heavier elements like neon-22 and give you longer cooling delays. So just to wrap up quickly, I want to make sure I point out that the carbon-oxygen phase separation stuff has been around for a while in the white dwarf literature and in white dwarf codes. But this is the first time it's been implemented in an open source code like Mesa, so that's kind of a big part of the motivation for what I've been doing. I just want to close by bringing it back around to Mesa to point out this is an open source software that all of you can use, either in your classroom through portals like Mesa Web, or you can download it and install it on your laptop. And happy to hear any feedback about the ways you're interested in using Mesa. I'm one of the lead developers on the Mesa team now. So anything that you're interested in doing, such as carbon-oxygen phase separation, this is in the code, it's a public code, and you can run these models yourself. So thanks very much.
Evan, you talked about the impact on cooling, but there is another potential observable, which is type 1a supernovae. And could the structure be inferred from mergers of white dwarfs?
From mergers of white dwarfs?
That trigger a type 1a. So obviously if you have a separation, you
Yeah.
get a different merger.
I might take that question a slightly different direction. We had some really fun discussions last fall at a KITP program about if this distillation is true, you're putting neon-22, like concentrations of neon-22 in different parts of white dwarf interiors, and that could really change the nucleosynthesis depending on kind of how the detonation happens, because neon-22 has a few extra neutrons, right? And so you're going to maybe go through different nuclear chains that way. I was actually just talking with Ken Shen about this like a week ago, and he said the results are kind of mixed on doing these sorts of calculations, but people are very actively thinking about. I don't think we discussed as much the sort of direct merger scenario, but we were talking more about the kind of still double degenerate where one, accretion from one white dwarf triggers the other to go supernova.
This is one of the unsolved problems still, how to trigger the explosion. In
Oh, yeah.
either scenario, it's not so maybe something to do with the phase separation could help.
Yeah. I don't know if the phase separation itself would induce a detonation necessarily, but I think there is some hope that it could leave some signatures behind in terms of supernova remnants and radioactive elements like manganese, for example.
Okay. other comments. Go ahead, Tony.
So rather than simple distillation, it seems to me this is zone refining, that which is the basis of all semiconductor technology. This is how you make ultra-high purity silicon, for example, is you take a bar of silicon and you run a liquid zone through the bar, moving it through the bar, and all of the impurities go to one side or the other of the liquid zone, and if you do this a whole bunch of times, you wind up with, 10 to the 15 pure silicon, for example.
Interesting. So if you go through the phase transition over and over again to separate further and further. Yeah, I think for most white dwarfs, they only go through the phase transition once, but I have wondered a little bit. You could imagine melting a white dwarf through binary interaction or something, and then maybe freezing again. So.
Zone refining.
Okay, yeah, I'll want to look up that term because I haven't heard it before.
Any other comments? If not, let's thank Evan.
Okay. Can people hear me? Okay.
Yes, it's good to have the mic.
Great. I'm a second-year PhD student at Boston University. I work with JJ Hermes in our white dwarf group there. And so unfortunately, I haven't run Mesa since the freshman year of my undergrad, but I will keep talking about white dwarfs. And I'm going to be talking about some work that JJ and I have been doing with Quiche Day to build up a sample of remnant planetary systems of white dwarfs that we think are showing evidence for collisions among planetesimals and the debris disks that they're hosting. And so one of the reasons we think this is going on is because a small fraction of white dwarfs show pretty convincing evidence for a dusty debris disk that they're hosting. So kind of like how Evan was showing, white dwarfs have this carbon and oxygen core, but their intense surface gravity leaves an outer envelope that is generally either pure hydrogen or pure helium. And so about 40% of these white dwarfs show pollution in the photosphere of elements heavier than helium. And so the model we have to explain this is there's some reservoir of planets and planetesimals like asteroids that survive post-main sequence evolution. During mass loss, there's going to be this phase of instabilities in their orbits, and so there will be dynamical scattering. Some fraction of these smaller bodies will be perturbed onto star-grazing orbits, where if they're launched within about a solar radius, they'll be tidally disrupted by the white dwarf. Eventually, you'll get a disk that circularizes and accretes onto the star. And if that disk is fortuitously inclined to us, we can probably see enough of those dusty effluents reprocess the starlight into the infrared. So I'm showing a pretty dramatic case here where there's just a huge infrared excess relative to the white dwarf blackbody, but that's illustrating the point. But this is pretty rare. Only 2% of white dwarfs show infrared excesses that are consistent with a dusty debris disk that's being accreted. One important thing about this sample is we see photometric variability in nearly all of them. So Andrew Swan did some pretty good work on this a few years ago, looking at these systems in Ys, and 70% of them showed significant variability in the mid-infrared. Notably, though, that you don't see that same variability in the near-infrared. So Laura Rogers looked, and on a 3-year time scale, they were able to rule out similar stochastic variability in the K-band. Now, the subset of these systems that I've become particularly interested with are a really rare class that show this infrared excess from a dusty disk, but also show a gaseous component in emission. And so we find these systems usually from the calcium triplet in the near-infrared. And it shows this characteristic double-peaked profile just from the rotation of the disk. the interesting thing is these disks have been found to precess on timescales as fast as a year. So over time, you can watch the profiles transition from this kind of equal point here to being blue shift dominated to red shift dominated, and we can map the orbital dynamics of the gas that way. But it's an open question why only 4% of these dust systems show this gas in emission. So we know these systems are variable in the infrared. And so that is probably a signpost for collisions among planetesimals within the debris disk. And so that should be liberating gas throughout the disk. So I like this diagram drawn up by Amy Steele from a few years ago. So there's a few mechanisms that could be producing this gas. It could just be sublimation from the innermost component of the debris disk, where the equilibrium temperature is sufficiently high to sublimate that dust into gas. Or you could have collisions that are producing gas at orbits further out than the sublimation regime. And so that's what we think is happening because we're seeing this variability. And so maybe that can illuminate why there's this discrepancy in the occurrence rate and the rates that we're seeing. And even more, maybe these collisional events can illuminate how the disk emitting area is changing, because that's what's driving the variability. A collision might liberate more dust and gas that can reprocess more radiation to the infrared and get brighter, or the opposite to get dimmer. And so that's what we've been investigating. For example, we know these systems can enter drastic brightening events. So here's one such case of one of these Gastus systems. We think a collision happened here that liberated all this extra dust to fuel about 2.5 increase in flux in the infrared. Notably, this variability was able to sort of overturn the canonical model that we were working with. So Mike Jura in 2003 proposed that these disks might be geometrically flat and vertically optically thick. But Andrew Swan and Scott Kenyon and others were able to show that this kind of variability can only be explained by an optically thin disk and collisions going on that disk. And so with the help of Quichelet, who's built this pipeline to extract light curves from the unwise images, we've been looking at all these Gastus systems, and indeed they show similar variability to WD-0145. And so here's just a sample of some of these 6 of these 21 known Gastus systems, showing pretty drastic brightening events and just generally stochastic variability. So we think by searching for white dwarfs that have light curves that look like these in the mid-infrared, we might be able to more efficiently grow this pretty rare class of stars. But we also might be able to learn a lot more about what's going on in these disks. So already just with 2 light curves here, we're able to learn that these disks are optically thin, partially because their flux is decaying linearly. We're also able to learn that collisions are going on because we see these infrared excesses now for decades. Whereas Poynting-Robertson drag, which is the angular momentum loss mechanism that's fueling accretion, should deplete a lot of the dust on a time scale shorter than 10 years. Yet we still see these collisions, or we still see variability, we still see infrared excesses, therefore there's probably collisions going on. But the brightening of these systems remains unmodeled, so we're motivated to keep finding them, keep growing the class, and not just wait for SCSS 5 to find a bunch more. But this isn't the only mechanism to probe collisions in these systems. So Uri Malamud, a couple years ago, showed that if there are collisions in the debris disk, some material should be pushed to wider orbits. And so if you have one of these debris disks that is inclined to be edge-on, you can see transits from that planetary debris. And we've only been able to find a few of these systems very recently with the launch of surveys like ZTF, TESS, finally getting long enough baselines to build up the sample. And in this one such case, WD 1054, we've been able to constrain the period very precisely to just higher than 25 hours. But as this red arrow is illustrating, there is a distinct piece from the bulk motion that is orbiting at a wider orbit at about 25.5 hours. So that material could have been perturbed to a wider orbit from a collision. So I'll wrap up there, but this is an exciting stage we're at. We've now been able to learn that these Gastus white dwarfs show this really characteristic high amplitude stochastic variability in the mid-infrared. And we're hopeful to continue to build up the known population to learn about what's really going on in these debris disks around white dwarfs. So I'll pause there and be glad to answer any questions. Thanks.
Thank you, Joe. This was very interesting. So if we just look at the solar system, right? We live in it, and imagine the sun becoming a white dwarf. I don't see an obvious path to populating that region, which is roughly a solar radius with collisions among the inner planets. I mean, it sounds more like maybe you make that debris after, from whatever envelope was shed from the star. So what's your take on that? I mean, is it really left over before, from the time before the red giant phase, or is it after?
Yeah, so if we use the solar system for an example, the sun will bloat to a maximum radius of maybe an AU. But mass loss during the giant branch evolution will push out the orbits of all the other planets. So surely Jupiter and Saturn will still be hanging out far in the solar system, and maybe the asteroid belt too. So I think to use the solar system, for example, there should still be a reservoir of rocky or planetary material to be scattered towards the white dwarf. As far as the material that's engulfed, like Venus, Mercury, potentially the Earth, I don't exactly know what will happen to that. Maybe radiation pressure and thermal pulses will push it out, as we see in planetary nebulae.
The amount of friction will bring stuff in.
That's true, too.
So that will clean up everything within the envelope of the red giant. But it sounds like it will clean up, but then you need to make it again. You see, because when you have the envelope, the dynamical friction time is really short. I think, if you check the numbers.
Yeah, I don't know, but I do want to check them now. But I think it's pretty safe to say that there should be a lot of material out there that survives and is safely far away from the maximum extent of the AGB star.
You need to bring it in. And
yeah.
My guess is you need to make it also.
Okay.
But check it out, because that's an interesting question.
Yeah.
What's the source of this thing?
Yeah. Yeah.
Okay. Other questions, comments? Oh, okay, go ahead, Josh.
What are the limits on mass in debris disks?
Yeah, so
Do they have any, estimates of how much mass could accumulate? Are there numbers that we should know about? The reason I'm asking is if you have conditions that produce a lot of rocky material and have significant mass, this might be a very interesting new way to lead to accretion-induced collapse. You only need, 0.4 or so in round numbers to get their solar masses.
yeah. So we
what do
we
know
think
about
that these debris disks, that the donor body likely had a mass on par with solar system asteroids. There's, I think, a few ways you can measure that. I think you can estimate it from the dust emission. WD 1145 is one of these sort of transiting debris disk systems. From modeling its transits, an asteroid-like body would have to, best explains the observations. I don't understand what's going on under the hood to calculate that, but what I do know is we think these are probably, they were asteroids that are creating these debris disks.
So altogether less than an Earth mass, and you just cannot do much to the white dwarf.
Mhm.
Unless you have a companion. That's
Certainly,
fancy.
yeah.
Any other comments? If not, let's thank Joe again.
Thanks.
All right.
Oh, shoot.
Thanks. You'll be thrilled to hear that I intentionally planned a short talk, because I knew this would happen.
Well, we like to hear you, so
Oh,
we're
yeah.
thrilled.
Oh, yeah. Oh, come on. Brilliant. So, can everyone see nothing? Perfect. Let's get started. So, the mystery starts in 1954, when Van der Hoest et al. Plot the 21 centimeter emission in galactic coordinates. So, galactic azimuth, that's right, and velocity up. Picture that in your head. That's what they found. It's a little odd. Don't think too much about what it means. But the gist of the plot is that already in 1954, people were thinking, oh, something's up with the galaxy. A few years later, they took the same plot, well, different day, but a different group took the same plot and looked at it from the top down and plotted the density as a function of galactic longitude and latitude. And they again found certain weird distributions going on in the galaxy. And then 50 years later, this plot got a major glow up where Levine et al. Took a really comprehensive H1 survey and plotted the same thing, but now in terms of galactic average height. So now the colors actually mean something. So the dark colors mean that some average plane is below z equals 0, and the lighter colors mean that it's above 0. So you can clearly see that on the left side, things are above 0. On the right side, things are above 0. Did I already say that? Below 0 and above 0. So if you picture that in your head, it's almost like the disk of the galaxy is going down on one end and going up in the other end. That's what we call the galactic disk warp. So you can imagine taking a ring around that center and then plotting the sort of average vertical height of the disk around this ring. And this is what you get, a very clean, beautiful sine wave. So again, x-axis is a galactic azimuth. So as you're looking from the galactic center to the right, to the left, you see on the left-hand side, the galactic disk is rising to 2 kpc. And on the other side, it's dropping down to 1 kpc. So this is all in gas. People have also found since as early as 1989, is it the right number? Yes, in 1989, that the stellar disk is also warped in the same direction as well. And this plot also got a major glow up recently in 2018/2019. When Chen et al. Plotted just the observed Cepheids in the galaxy, again in their galactocentric coordinates, and found that there's a striking rising towards the left and dropping towards the right in the stellar disk as well. So if that's not enough to convince you that there's warp in the disk, here's some other examples. All right, warps discovered since 1957. We got it in red clump stars. We got it in CO. We got it in H2. We got it in Cepheids, different group. We got it in Gaia. If it's in Gaia, you know it's real. And finally, this year, we got it in mirror variables as well. And these are just some of the examples. We still have more red clump stars from more groups, pulsars, and dust. The dust is warped. Like, come on. So basically, the point is that everywhere you look in the galactic disk, there are warps. And this is a real image of me first learning about this, tell it to my advisor. The disk is warped. So if it's so prevalent, what causes the galactic disk warp, right? Unfortunately, since 1960 to present day, there's been 1,000 papers written on the galactic disk warp. 1,000 papers, that's a paper a month for 60 years. Ivanov couldn't do it. So here are some of the most popular opinions of what the warp might be caused by. So we have tidal forces, misaligned gas accretion, vertical oscillation, bending modes, quarter polar torque from outer halo, massive halo perturbation, ram pressure stripping from the local group. The list goes on.
But the important part is none of these models have actually quantitatively reproduced what we observe for the galaxy. And because we have a few minutes left, let's just focus on one of them, shall we? The tidal force from the LMC, or the Large Magellanic Cloud. So it turns out this actually was one of the first, if not the first, methods proposed to warp the galactic disk. So in what is sort of considered as the original warp paper, in 1957, Kerr points out that a phenomenon, the warp, could be caused by something like gravitational tides. In the same year, a few months later, Burke et al. Also say that this event, the warp, can be caused by gravitational tides as well. And even furthermore, they say that the direction of the warp is actually along the direction of the LMC, which is intriguing. But both of these papers actually point out the fact that, according to back-of-the-envelope calculations, the amplitude of the observed warp is way too big to be from the LMC. Now, at present day, the envelope has gotten much larger with a lot more CPUs and even GPUs. So we can go and actually test this claim, right? So this was our favorite plot of the warp, where you can clearly see the amplitude of the warp. And what Chervin Laporte et al. In 2018 have done is they've taken an LMC, or realistic LMC, they've taken a Milky Way and tried to make them collide, not quite collide, but taken as a first infall, and evaluate what the warp actually looks like. So black line is the data from H1, and the red lines are just models from the LMC that I've sampled. You might notice that one of these two things are much smaller than the other. So in particular, the red line, which is a really, really massive LMC, 2.5 times 10 to the 11 is at least 50%, if not twice more massive than what we think the LMC actually is. It doesn't account for 1/5 of the actual observed amplitude. Even more, if you look at the actual shape of the warp, so going into the right panel now, from the top-down point of view, the LMC induces more of this sort of snail-like spirally pattern, versus the H1 observed disk is nicely tilted, not too much spiral-y things going on. Right. So the LMC certainly does induce a warp, because we do see it. But it's just not going to be the dominant effect of what's driving the warp. Two reasons: the amplitude is too small, and the shape doesn't look right. It's pretty good reasons. So flashback to last fall, where we presented some exciting results about the observation of the stellar halo. And we found that the stellar halo seems to be tilted with respect to the galactic disk at around 25 degrees. So a really fundamental question is, if you take that shape, convert it to the dark halo, and create an orbital potential in that, and integrate some disk-like particles in that potential, what happens to the disk, right? So here's our back-of-the-envelope animation. So now what you're seeing is you're seeing a bunch of disk particles initially circularized on circular orbits, and now they're going to be colored in terms of their vertical height. Red means it's above z equals 0, blue means it's below a vertical z of 0. So within the first 2 gigayears already, you see the onset of a warp-like structure happening, and by 3 or 4 gigayears, it reaches a point where it matches the amplitude of the observed disk warp. Okay, so this is fine and mesmerizing, but what about actual plots, right? All right, that's enough. So let's go back to this nice little chart where we have the observed galactic warp at black lines. We have 2 LMC models, and then we have the sort of disparity between the 2 amplitudes. So this is what you get if you just plug in that tilted halo model with no fitting, with no tuning. The first thing you notice is, sure, it's not the exact same shape, but come on, the direction is nearly spot on. More importantly, the amplitude is nearly correct. And now what's more intriguing is if you take these 2 curves and you add them, like 1 plus 1 equals 2, or in this case, more like 10 plus 1 equals 11. Ta-da! So what I'm trying to say is not that the actual effect of these 2 models is an addition. What I'm trying to say is that if you take a tilted dark halo model, it generates a warp at the amplitudes that we observe today. And if you add in the effect of the LMC, you get something that looks very close to the observations. So there's one more mystery that we need to solve. We've talked about galactic dwarfs, nice and all, but there's also the issue of the galactic disk being flaring. Now, flaring means you take a nice thin disk, the thickness increases towards the outer galaxy. So this has been also observed So now we're plotting in black lines the observed warp and the observed flares of the gas disk and the stellar disk. And in colored lines, we're plotting just the model that comes out when you put in a dark tilted halo. You can see that all four seems to line up quite well. Once again, I'd like to remind you that this was not a fit to the data. What we did was we took the stellar halo parameters for measured Hanedal 2022, plopped it into the galactic potential, and see what happened. So this is what we like to call a zero parameter fit, I suppose. So here's the TLDR. First, the Milky Way's disk is warped, and we've known that it's been warped since 1957. That's a long time ago. No theory so far has quantitatively reproduced the warp and amplitude and the flare of the disk. Recent evidence, independent of this, shows that the stellar halo is tilted 25 degrees above the galactic plane. And adopting this sort of zero tuning model into the dark halo, we convincingly reproduce warp and a flare. So might I claim that the mystery of the warp is unwrapped, or should I say, unwarped? Thank you. I'll take it happy questions.
Jesse, one issue to consider is obviously the halo is in a fluid state. It's not like stationary the way you assumed in the simulation. So you assume that this structure is there, but on a dynamical time, it could be influenced, like Sagittarius dwarf galaxies passing and things like that. So how long does it take those disk particles to respond to changes in the halo?
All right, so that's a multiple-fold question. So the last question, it takes around like a giga-year maximum for the disk to catch up to the halo. With regards to the changing of the halo, you can actually play with different models by making the potential change. We've also looked at n-body simulations. And it does seem like you could maintain the tilt of the dark halo over like much longer periods than 1 giga-year. So there's plenty of time for the disk to warp.
Charles?
So Jesse, you and Charlie and many people, you look at the stars and you infer from that the dark halo. So how robust is that connection?
That's a great question, Charles. Oh no. All right, so that was the one plot that I forgot to include. So if you take something like TNG50, that we all love and care about here, and you plot the tilt angle of the dark matter halo and the tilt angle of the stellar halo, it's like a very nice tight one-to-one line. This is not that plot, but it's the closest thing that I had to here.
The basic reason is that both are collisionless particles.
Right,
Yeah.
exactly. And they all come from the same merger events, the halo.
So it's basically the potential is distorted, and then all the collisionless particles respond to that.
Right, absolutely.
Any other comments or questions? Morgan?
It's really fun to think about. One thing I was wondering is, once the structure is tilted, then it might be interesting to think about the effect of the LMC again, because there's sort of the nonlinear coupling of once you're out of the plane of the disk, then
Right.
the tide pulls on you more strongly. And so it might be the case that there's aspects of that that aren't the completely separable ones, which I'm sure you've thought about, but
Absolutely.
it's really interesting to think about the fact that once you're distorted, you can enhance the effect of that.
No, 100%. It's
Yeah.
not going to be a sum,
Yeah.
but it's at least a sum.
It looks like you had some more memes that you didn't have it.
All right, so basically what I wanted us to end on was 957, Karen Berg says, wait, it's all tilted halos? And yes, me, Charlie, and Lars think it was always tilted halos. Always have been, kid. Wait, that's the last meme. Thanks, Kareem.
Thank you, everyone. See you next week.
Cool. Yeah. Oh.